Today, I'm going inside Avalanche Energy, a startup in Seattle building small nuclear fusion reactors. Nuclear fusion is one of the most promising energy production technologies on the horizon, but every approach has difficult trade-offs and drawbacks. Avalanche is focused on going smaller. They aren't trying to replace massive nuclear fission reactors or hydroelectric dams. Instead, they want to build a portable fusion reactor that can be used in harsh environments, like underwater or deep in space. Basically, if it works, it'll just be like the most efficient battery ever created. I wanted to see the Avalanche facility in person, so I flew to Seattle and got a tour from the CEO, Robin Langtry. Okay, there's a ton of technical stuff to explain here, so let's start with a quick overview of the nuclear energy landscape. There are two key types of nuclear energy production: fission and fusion. Fission is when you split an atom, usually uranium or plutonium, and it releases energy. Nuclear fission is very well understood. Robert Oppenheimer used fission to create the first atomic bomb at Los Alamos in 1945. And we've been using nuclear fission plants to generate electricity for decades. The United States actually gets 18.6% of its electricity from nuclear fission facilities. Now, fusion is the opposite process. You're still operating on the atomic level, but instead of splitting atoms, you're fusing them together. This also releases energy. One of the biggest benefits here is that you don't need to use a lot of heavily radioactive materials. Instead of uranium and plutonium, fusion usually requires elements like helium or boron. The problem with fusion is that it requires a ton of energy to be introduced into the system in order to get those atoms to actually start fusing together. So even though the technology is promising, the fusion industry has yet to actually go and build a device that creates and maintains net energy on a large scale. But there are two reasons why we know for a fact that the science behind fusion works. First is our sun. Gravity from the sun applies immense pressure to hydrogen and converts it into helium, which releases the light and heat that makes life on Earth possible. The second is the hydrogen bomb. These have been tested and are known to produce predictable fusion reactions. But both the fusion from the sun and the fusion from a hydrogen bomb are uncontrolled reactions. We haven't been able to bottle them up and convert all that energy into anything usable as electricity. So the fusion industry has been working on creating a device capable of sustainable and controllable fusion reactions for decades now. It's clearly an immense challenge, but there is some cause for optimism. Major projects are starting to scale up now, and the scientific community has hit a number of significant milestones. Before we go into that, there's still the question of how Robin actually wound up in this position in the first place. There really aren't all that many people working in the nuclear fusion industry. So what led him to start this company?
Grew up in Ottawa, Canada, went to undergrad and master's at Carleton University. And so I ended up moving to Germany and doing a PhD in turbulence modeling and transition modeling in Germany while working in Munich. And then ended up at this little space startup south of Seattle that nobody had heard of at the time called Blue Origin. That's where I met my co-founder, Brian Weird.
I met Robin writing proposals for the founder of that company for a new rocket program. We ended up hanging out, talking about these papers, but just had a shared interest in technology that we believed in and wanted to move towards. At one point, we started looking at fusion companies, just comparing notes, what excited us, and how do I vet, what fusion company is going to work? Who's going to do it? How do I know?
The experience the team had at Blue Origin was really critical for setting up the plan for Avalanche. Even though building rockets and building nuclear power might seem different, there are a bunch of transferable skills. You need to think from first principles. You need to use physics to calculate how a system will function before building it. You also need to be able to manufacture something massive and do it safely. But from talking to Robin, I think the most important lesson he took away from his time in the space industry was actually the economic realities of manufacturing at scale. Back in the 1980s, the space shuttle was the most advanced rocket system ever built. It was massively powerful and also massively expensive. The total project cost was over $200 billion. When the commercialization of space began in the new millennium, there was no way for small startups to raise billions for risky projects on day one, so they started smaller. Two space companies started around the same time, Blue Origin in 2000 and SpaceX in 2002. Both have accomplished incredible things, but SpaceX has been able to send more than 10 times as many rockets to orbit in the last 20 years. There are a lot of possible reasons for the difference in performance, but one theory is that SpaceX chose to focus on developing smaller, more modular engines. A single Raptor engine is less powerful than the rocket that took the shuttle to space, but grouping 33 of them together created the most powerful rocket ever built. By going smaller, the SpaceX team was able to iterate faster on engine development and create a product that was both reliable and affordable. Robin saw this play out firsthand. After all, these were his direct competitors while he was at Blue Origin.
One of the things we learned working at Blue Origin was like the importance of size.
If it was too big, you didn't have the machines to make it, you couldn't get them, they had to be custom. Your supply chain was small, the cost went up, and anything that took a lot of time or money meant that people didn't want to say yes yet. They weren't confident. They were like, let's think about it more.
Going smaller has a ton of advantages. Individual parts are smaller, so they can be moved around with forklifts instead of massive cranes. The supply chain is more reliable. The factory is a safer environment. All of this enables speed of iteration, which ultimately creates a better product.
So we said we need to have a robust supply chain. We need to remove as many barriers of entry for new people working on this. And what we really thought needed to happen to Fusion is what you're seeing happen with successful startups other places, where they're able to move fast. How do you make Fusion move fast?
So Robin left his job at Blue Origin to set out to build a nuclear fusion reactor that's smaller than a washing machine. Before we dig into Avalanche, let's go through a quick history of nuclear fusion development. We've actually understood the basic idea of nuclear fusion for nearly 100 years. Arthur Eddington and Robert Atkinson were two physicists studying the stars in the 1920s and proposed that nuclear fusion could be the underlying mechanic powering the solar system. In 1934, Ernest Rutherford successfully fused deuterium into helium in an experimental setting. The goal here wasn't to produce energy directly, but it helped understand the chain reaction that was going on in the sun. During World War II, Edward Teller proposed using hydrogen as fuel to increase the power of a nuclear explosion. You might remember seeing this in Oppenheimer. The idea worked, and on November 1st, 1952, the United States successfully tested the first hydrogen bomb. In the 1950s, research split between weapons development and energy production. Two Soviet scientists developed a design for a magnetic confinement fusion device called a tokamak. And this tokamak style of reactor is still in development to this day. Essentially, every fusion reaction needs some sort of force to push the atoms together. In the sun, it's just gravity, very simple. But if we're going to do fusion here on Earth, we need to apply some sort of external force, and there are a few options. The tokamak device I mentioned, it uses magnetic confinement. The fusion material is in the shape of a donut or torus, and then subjected to immense magnetic force in order to trigger fusion. Tokamaks are the most popular reactor design, with over 200 built since the 1960s. There's even a $25 billion project underway in southern France that's expected to be operational in about a decade. These are massive devices though, and there are lots of kinks to iron out before they start producing real energy at scale. Another notable approach to fusion reactor design is the field reversed configuration. You might have seen a company named Helion working on developing this technology. The device essentially generates two separate plasmas in ring shapes and then shoots them at each other to trigger the fusion. It's really fascinating to watch in action. There are other designs as well, like inertial confinement fusion, which basically just involves shooting dozens or even hundreds of extremely powerful pulsed lasers or ion beams at a small fusion fuel pellet. The compression heats up the plasma faster than it can radiate away, which produces fusion. And there are hybrid approaches that use a combination of technologies to create the conditions for fusion. Avalanche is using a new design called the Orbitron. The entire device is much smaller than other fusion reactors and relies on confining ions using high voltage instead of high-strength cryo-cooled superconducting magnets. I'll let the team describe exactly how it works.
So the way we're doing fusion, it's a hybrid, right? It's magnetic confinement of electrons, electrostatic confinement of ions. So what we do is we have a cathode, basically a rod, that we energize to really high negative voltage. These are our high voltage power sources. So, this takes wall plug power, 120 volts AC, rectifies it up the ladder, comes up over the ceiling, and then drops all the way down. So high voltage comes in, energizes that cathode inside. Then this makes 2 milliamps of beam current and then extracts that plasma and accelerates it down the beam line. And then once the beam goes in, it sees the high voltage from the cathode, and it gets wrapped around the cathode and starts orbiting.
And as they're attracted to it, just like a satellite pulling into orbit around Earth, it'll go into orbits around it, but it goes axially as well as azimuthally. And to be able to get, so we're trying to hit that energy, is you can get that speed going, and then you drop them into that potential well. And the higher the voltage this is, the faster they'll be going when they go whipping around this.
And where those orbits are crossing, the ions are crossing at such high energies that they'll fuse. And so you can do fusion that way. The problem is if you don't have electrons, you're gonna hit what's called a space charge limit. So you're gonna get so many positively charged ions rotating in there that it overwhelms the negative voltage of the cathode that's holding them in their orbits.
And that's a problem because like charges repel. So that presents a fundamental limit of how many ions you can actually introduce into your orbitron. To combat this, we have tried to mitigate that space charge limit with electrons. And so these magnets here form a magnetic bottle. And what that bottle does is it traps the electrons.
And so when we co-confine electrons with the ions all spinning in the same direction, we can cross that space charge limit and we can get to a really high plasma density. And so once you get to that high plasma density, you're making a lot of fusion. In this case, the fusion products would fly off the plasma, hit the walls, heat the walls, and then we would run a working fluid through this heat exchanger to extract the energy as thermal, and then run that through a turbine to make electricity. And then the penultimate version of this would actually have direct energy extraction, so directly converting the charged particles to electricity.
In the end, the device is going to feed itself. So a net energy generating device will be just like your car. It'll have a battery, it'll start up the engine will pump back and charge up the battery, and then it'll feed on itself that way. So same kind of thing, except your fuel isn't going to be a hydrocarbon, it's going to be a fusion fuel. It's going to be deuterium and tritium in grams that could last you many, many years.
If this works and Avalanche is able to create sustainable fusion in such a small package, the applications are really interesting.
Our value proposition in this case is extending the operational range of military platforms, units, weapon systems, whatever, in any domain. So that's deep sea, that's space, that's terrestrial, really anywhere where weapon systems require energy to persist, to operate, by delivering them the capability to access energy on demand at the point of need.
We would really want to fill the niche of smaller, more compact energy sources. So that could mean things like small autonomous underwater vehicles, which is actually a great place for fusion. You have to worry a lot less about any of the radiation coming off of the reactor, since those vessels could be unmanned. One thing I think would be really cool is if you could use it in disaster relief situations where there's, you can't plug into the grid because the grid doesn't exist, but you could still bring power to people. That would be a really altruistic and amazing application of it. But filling in those gaps where it wouldn't be grid power, but it's something where you need to use it remotely for extended periods of time.
There's a lot of really interesting, varied approaches to fusions. They all have sort of pros and cons associated with them. I think what we're doing, sort of hybrid magnetic electron, electrostatic ion, is really interesting because it just scales down so small. So like this is a full-size version of what we're actually building and testing in the lab. And so that lets us basically be super capital efficient. This does not take $1 billion to build. This is like maybe 100K at most. And it lets us iterate really fast. So it lets us follow this sort of like SpaceX test, fail, fix approach to doing fusion.
Even though Avalanche specifically set out to build a product that could eventually become mass manufactured, this project is extremely ambitious, and it certainly isn't cheap. So I wanted to know how they got the company off the ground.
So we've got a lot of network in the new space, and through our network, people said, hey, you got to talk to Avalanche, and we were brand new. We'd just gotten out of space.
There was no Series A pitch deck. There was like a collection of slides that were sort of left over from the seed, plus some stuff that I just kind of like made for investor updates. Like I remember like the ones that I really, really wanted to work with, which was lower carbon, founders fund, And so I was really honored, like, when we got a chance to actually like pitch Scott at Founders Fund for a second time. I think the key thing was like, okay, this is interesting. Like, you should come out to Seattle and come see the lab. And I think that's really what made the difference.
Startup is stressful and exciting. It is a team building your road as the other team is accelerating the car. Probably 6 weeks from running out of money, we were able to land our Series A. As soon as we landed that money, I quit our jobs already in anticipation. And then it was, who are we gonna hire? How do we talk to them? How do we talk about this? How do we talk about something so futuristic, but make it real enough for people to join us on that journey?
In order to understand what goes into funding a company like Avalanche, I sat down with my colleague Scott Nolan, who's a partner at Founders Fund, to talk about why he decided to invest.
So we'd met with a lot of fusion companies over the years. Many of them were using a tokamak design, which is the big donut that people think of. The tokamak fusion designs benefit from designing something very large and going and building something very large to prove the performance and to get net energy out, and will require billions of dollars to build. Avalanche, on the other hand, took pretty much the opposite approach. Avalanche's design uses a strategy that is where you're combining a couple of different technologies to break through a natural limit on how many particles you can jam together. Avalanche believes, and they're proving through their first devices, that they're going to be able to get past this barrier by offsetting space charge in a pretty unique way. You know, there's a bunch of companies going after very large scale fusion, and that could work, but I think those large scale fusion reactors are going to have to plug into the grid, and when doing a startup that's producing energy, I don't like plugging into the grid. I like being somewhere very remote, where a small customer could pay a high price for the energy. Avalanche follows that same strategy that Radiant does, which is, can we unlock new greenfield applications of energy where you couldn't previously have it, and where you might be willing to pay a lot for it.
Fundraising is just one small part of building a startup, though. In order to get their first reactor up and running, there were a ton of problems to solve and engineering challenges to work through.
There's 3 ways that I think about building the company, generally speaking. There is the simulations that are going to be able to, you can explore a lot of different space virtually. Then there's a part of the company that actually has to build it and then try to get it working to correlate to the simulation. But a simulation, you can probe anywhere in the device and understand what's happening there. The missing other part is diagnostics. So you have to simulate it and predict it. You have to build it. Then you got to close the loop to see how your simulations were working in the beginning. We found this guy out in Oxnard, California, and he had a big warehouse full of stuff. And getting down there, we said, hey, we want to see all the vacuum science, fusion, none of this stuff was really going to make sense to him. We said, you have a bunch of stainless steel stuff? Yes. Where is it? Well, it's up front. It's the prettiest looking stuff, and I've been leasing it to Hollywood for props and sci-fi films. That's where we got a lot of our original equipment. He thought, evidently, you make CBD oil out of this stuff too. So he was pretty convinced as we shared some shawarma out by the Penske truck we rented. He was asking about our CBD oil company, and that's how we found out that most of the people that were buying that equipment is what they were using it for. For the next, 800,000 miles, we stopped at about every Home Depot on the way to get tools, to disassemble, to strap it down as old experiments rattled themselves to death in the back of the Penske.
As we got further into it, so we're starting to do fusion and stuff like that, but we're starting to realize there's some really key KPIs, and it's really hard to work on them all together on one single machine. We have to scale up our voltage to 300 kilovolts. We have to scale up our magnetic fields to half a Tesla. We have to scale up our beam current to milliamps. And it became really challenging to try and just do that all on a single machine. It was that realization that to go faster, we needed to break the problem apart and let those teams basically go work their individual things. We're limited in terms of how much power we can put in from the power sources, and things just heat up and get hot. So you don't want to melt the machine, obviously. And then it's going to be a process of okay, how do we make this more efficient so that for the same amount of fusion out, we don't have to put so much power in? And then at the same point, how do we jack up the amount of fusion out?
The opening behind me was a wall when I joined, but it was blown out shortly after I joined, and we expanded into this other room. There was only one test chamber or test cell Now we have 3. I was the 15th employee, and I believe we're just over 40 now. So we've grown in team members and in physical space that we're occupying.
So we said we need to have a robust supply chain. We need to have small components. We need to have tools that we can get readily, that people are familiar with, that don't require special training. We need to remove as many barriers of entry for new people working on this. And we also need to remove the fear that comes with a decision to be able to act. How do you empower people to act other than to say, you have to make this decision, as you can make the consequences of it way lower. And that all came to scale.
There's still a ton of engineering work that needs to be done in order to really get these fusion microreactors working, but the team is optimistic about what comes next.
I do believe the next Q engineering greater than 1 fusion machine is probably going to happen in the next 5 years. I think it's going to be really awesome. Getting to like a plasma density and making a lot of fusion is really the next major goal for the company. Raising the next round and really going at Q greater than 1 with deuterium tritium is where I'm really excited to go next.
Right now is a good time to be working on it because there are a lot of small companies, and it's a time where people can be very innovative because there is money going into it, and you're not doing it for the sole purpose of studying it in an academic lab. We really do want to get net energy positive out at the end, so our motivation is higher to move quickly. So it's a good time to be working in it because all of these things are happening right now, both the money and a lot of different interest in it, and the ability to share information.
One of the problems with fusion, I think problems with running any company too, is you can set a really big mission that people get behind, and then when on a big mission, it takes big effort, and that takes a long time. And what we hadn't been good about, we still aren't great about, is celebrating, creating arbitrary milestones along the way that are both like meaningful and tough to get to, and also like some we can all agree on, that we say like we are actually making this progress towards the big goal.
I love hearing about novel approaches to hard engineering problems like this. The Avalanche team is working on something incredibly impactful and breaking down the problem in a really innovative way. Hope you enjoyed learning about the company. Stay tuned for the next one.